We're still talking about predicting chemical formulas using electron configurations. So let's look at another example here. We have neon. You know it ends in 2p6. It's in the second row. It's in the sixth column of the p block, so it's 2p6. And it has a valence of 8. The 2 plus the 6 gives us 8. So magnesium wants to achieve this configuration, but it has a valence of 2. Now we know that because it's in column 2, it's an alkaline metals. And how is it going to get a valence of 2? Well, if it loses these 2, as you can see, it's going to achieve neon's configuration. It wants to lose 2 electrons. What about fluorine? Well, fluorine's in the 17th column, and we know it has a valence of 7. So fluorine wants to gain 1. So that's not a perfect fit. Earlier we talked about sodium wanting to lose 1 and chlorine wanting to gain 1, and they came together in a perfect fit. So it was a 1-to-1 ratio for their formula. But here we have a situation where one element wants to lose 2, but the other element wants to lose 1. Well, let's see if we can figure it out looking at something like this. Magnesium has a valence of 2. I'm going to show that with 2 dots. So it wants to get rid of those 2 dots. Each dot represents an electron. Fluorine has a valence of 7. So I'm going to put 7 dots around fluorine. Now what's going to happen is magnesium, fluorine only wants one of these 2, so it's going to give up its 1. And now this fluorine has a valence of 8, so it's happy. But this magnesium still has 1 electron to give up. So what do we need? Well, we need a second fluorine. And that looks something like this. So this electron here is going to be donated to this fluorine. And what's our ratio? Well, it's 1 mg for every 2 fluorines. So our formula is MgF2. So knowing the electron configurations is a great way to predict chemical equations. Now, simple chemical equations. Binary chemical compounds is what we are talking about here. In other words, elements that, or compounds that only contain 2 types of elements. Well, what about, let's do a few more. Let's say we had sodium and nitrogen. What's the valence of sodium? Well, it's in the first column, so it has a valence of 1, so 1 dot. And the valence of nitrogen, it's in the 15th column, so 1, 2, 3, 4, 5. I'm drawing the dots separately. You don't have to do that really. There is a reason behind it, but we're not going to get into it here. Sorry about that. So let's see. Sodium wants to lose 1 electron, but nitrogen needs how many more? Well, it has 5. If the magic number is 8, then it's going to want to gain 3. So that means we need how many sodiums to satisfy our 1 nitrogen? Well, let's think about it. If we had 3 sodiums, each with a valence of 1, 1 electron would go there, let's make it go over here. One electron would go there, and one electron would go there. Now, is this nitrogen happy? It has a valence of 8. Have all these sodiums lost their 1 electron? They have. And how many sodiums do you see? I see 3. So, sodiums to nitrogens ratio is 3 sodiums for every 1 nitrogen. And that's your formula for sodium reacting with nitrogen. And we'll do one more. Let's say we had aluminum, valence of 3, so I'm going to draw 3 dots. And let's say we had phosphorus. So what's the valence for phosphorus? It's in column 15. So 5 dots. And what does aluminum want to do with its 3 valence electrons? It wants to lose them. What does phosphorus want? Well, it has a valence of 5. So what does it want to do? It has 5 and wants to gain 3 more to make a total of 8. So this is what we call a perfect fit. Aluminum is going to donate its 3 electrons to the phosphorus, and the ratio is a 1-to-1 ratio. So the formula is ALP. No need for any subscripts because 1s are understood. Hope that clears things up for predicting formulas. There is another way to predict formulas, but we usually learn this way first before we move on to just this swap and drop method. Alright, so that's part 9. Part 10 coming up.